So the thing about risk is that usually when people are approaching it, they're approaching it from either a compliance standpoint or from a security standpoint, and it's usually very dry. It's very, very serious and it's very, very important, but from that standpoint, you don't get the same kind of passion around it as you do with other things. My background is I've been an architect and engineer for the last 20 odd years. I'm approaching risk from a very, very different perspective. And I'm doing it in such a way that it expands the way that you design infrastructures and look at the way that the components actually fit together. So it's a lot greater than just risk itself, but that's what I'm going to use as a segue to go into the talk itself. So first off, I have a question for everybody here. It's probably fairly easy, but how did you get here? How did you get into this room itself? You probably walked down the hall, you're staying in the hotel, you came down the stairs. There's a sequence of events that took place in order for you to come over here. A series of decisions took place for you to get from your house, commuting over here, into the building, and into this room. Sometimes there's some random events that happen. Maybe there's a traffic jam. Maybe somebody walked in front of you and you had to change your route. Things happen, things occur that change the way that you get from one place to another. And then, of course, there's external conditions. There's things that are out of your control. Perhaps it's raining outside, and that's going to cause you to get an umbrella or take a taxi instead of walking. So there's a number of different things that change the way that you got from your home to here. Now, let's think about your infrastructure that you manage. How did your infrastructure end up being in the current state that it is? If you think about it, when it was first built, there was a series of decisions that took place. There was a plan in place in order to provide certain services and certain applications. Along the way, certain random events occur. Maybe there's a merger, maybe there was a hardware failure. Things change a little bit. And there's also external conditions. So if you think about it, your infrastructure is very much an organic thing. It's something that is not static. It keeps on changing, just the way that where you end up in life keeps on changing. You can guide it. You can give it some sort of plan, but it's something that's dynamic, that keeps on evolving and moving. Now, what if you could see into the future? And you knew all the different things that were coming along. You knew that it was going to rain. You knew that there was going to be a traffic jam. Then you would know to change your route. You would know to carry an umbrella. You would know the things that you need to do in order to compensate for the things that are going to occur. The same thing is true with infrastructure. If you know what's going to happen before it happens, then you can change the way that you design, change the way that you plan, and change your long-term strategy for an infrastructure. So what you're going to get from my session here is a different perspective, a different way of looking at things. It's not your typical sort of session where I'm going to show you things that I do or certain ways of doing things. I'm going to try to expand your mind to look at things in a different way, in a different context. I'm going to be taking parallels from different industries, whether it's medical or the energy system or pharmaceutical. Different industries have different ways of dealing with things. And I'm reaching outside of IT in order to create some parallels, in order to look at infrastructure in a different way. Then we're going to look at frameworks and how you can use frameworks to guide the way that you design your infrastructure. And then along the way, hopefully you'll get some new methods to add to your toolkit so that you can approach your new designs or your existing designs or your existing infrastructure in a different way from a different perspective. So I'll tell you a little bit about myself. I'm a solutions architect slash engineer. I do about 50% of one role and 50% of the other, depending. The reason for that is because I really like design, but I don't want to lose touch with the actual technology itself. So I like to have my hands on things. So I do architecture, I do engineering. Sometimes I do the full life cycle of a project. I even do pre-sales along that. But design is my main focus. I am one of the leaders of the Toronto VMware Users Group. I was also a leader of the Vancouver Users Group as well. I'm from Canada, by the way. I've gone all across the country, but I'm currently in Toronto. I was also an instructor over at the University of British Columbia, dealing with security, storage, cloud fundamentals, a number of things to get new students inspired and passionate about a career in IT. I did the same sort of thing at the British Columbia Institute of Technology. I'm currently a double VCAP, so that's a VMware Certified Advanced Professional in data center administration, data center design. I'm also very focused on software-defined networking, specifically VMware NSX. And I'm also an advocate for Nutanix as well as other hyper-converged solutions out there, vSAN and so on. And I'm an author as well. And I'm going to be publishing my, interesting. So I'm going to be publishing my first book in the new year, and I'll talk a little bit more about that later on at the end of the talk. So some of the organizations that I work with are international banks, government, power distribution, utilities, for municipalities as well as long-haul distribution generation, and healthcare and medical service providers. So these kind of organizations are the kind that they have a certain responsibility to the people that use their infrastructure. It's an obligation to not just their users, but also to the public and to the government and regulatory bodies as well. So these types of institutions need to make sure that their applications and their services are up 100% of the time. There is no wiggle room for downtime. Otherwise, it's a very, very critical issue. It could cause issues with power, which may cause issues with health, may cause loss of life, so on. So it's very, very critical that these sorts of infrastructures stay up all the time. Now, a commonality that I found with all these types of organizations is that when they go to design their infrastructure, they do so by utilizing a certain framework. There's many, many different types of frameworks out there. There's TOGAF, there's Zachman. From the server side, there's ITIL, there's many other ones. Every type of framework provides a certain something. There's no one that's better than others. There's just different situations that they may work with. So what is a framework, really? A framework is something that has a structure. It has a methodology, a certain way of doing things. The key thing is that it's repeatable. You know that if you follow this framework, you're going to end up with the same result every time. As long as you follow all the steps, all the processes, you can take this framework and you can apply it to multiple situations, and you know what kind of goal or end goal you're going to come out with by following these steps. But the key point is that it's a guide. It's not a law. It's not a step-by-step manual. This is how you do things. It's a way of organizing your thoughts and organizing the decisions that need to be made to come out with a solution that fits the requirements of whatever you're working on. So what happens when you don't have a framework? This is when things go bad. Now, depending on the environment, It may be something like an outage, you have a few customers that can't access the website, or it may be something critical where you don't have a contingency plan in place. The larger an organization gets, the more critical it is that they have a method of doing things, a method of planning, a foresight, contingencies, and knowing all the responses to every type of scenario that they're going to encounter. If you don't, then you may not just end up with something bad like this. You may end up with something worse, like this. Grizzly bear with shark arms. That's a lot worse than a truck with a little bit of fire coming out of it. And it's usually in these types of scenarios where you have bears with sharks for their arms and fire everywhere, that things don't really get much better at that point. Usually they get worse. That's when you know you're in real trouble, and you'll be thinking back to this talk, and you'll be thinking, why didn't I use a framework on my infrastructure? So one of the frameworks I'm going to be talking about is the VCDX methodology. Now, this is a methodology that was created by a number of different people within VMware. One of the key people right over here, VCDX001, John Rashid, was instrumental in creating this framework. And it can be applied to not only VMware products, but to architecture in general. It's a methodology that you can use in order to organize your thoughts and organize your plan of action, and you can use it in just about any type of scenario. So I'm going to go through some of the different design characteristics that are key to the framework and what they actually look like. Now, if you're going through the process of designing an infrastructure and there's a number of different components to it, you have to think about each one of those components and how can you apply these design characteristics to them when you're going through the planning process and the documentation process and so forth. So those are availability, manageability, performance, recoverability, and security. From an availability perspective, some of the things that you need to consider are high availability technologies, load balancing, application clustering, heartbeat configuration, the type of hardware that you use. Is it resilient? Does it have multiple power supplies? Does it have lockstep processors in place? Can you lose half of the equipment and still be running a single process? Now, when you look at manageability, how are you actually going to manage this component or this part of the infrastructure? Does it have a web interface? Does it have a CLI? What about a centralized management console? Would the management console manage just this, or would it actually manage a number of different things? Would you use a vendor-agnostic one, or would you use a vendor-specific one for this technology? Would you access it through an IP KVM so you can get directly over to the console? Or would you use something like remote shell execution, PowerShell, a scripting language like that in order to manage it? Or if you're connected over to Active Directory, would you use group policies to manage it? What about configuration management engine? Ansible, Puppet, Chef. All these things can be used to manage your environment. And these are the types of things that you need to consider when you're deploying something under manageability. Or are you going to use multiple element managers, one for each individual one? If you do, sometimes that can be a little bit difficult to manage. Not impossible and not necessarily wrong, but just more difficult to manage. If we look at performance, what about network bandwidth? What type of bandwidth do you have available for this specific part of the infrastructure component? Are you making use of aggregation? Is the component flash accelerated? Are you using an all-flash array, or does it have flash caching in the environment? And what type of workload are you actually putting on this? It is important to make sure that whatever workload you're putting on environment is specifically designed for that. It is possible to have general computing environments that are able to run a number of different workloads, but that doesn't necessarily mean that they're going to run them well. If you're worried about performance or you're concerned about performance and want to optimize the utilization of hardware that you have, these are some of the things that you need to consider. As the infrastructure grows, what sort of bottlenecks are you going to run into that are going to affect performance? Are you going to have a SAN that has a single controller that may start to get a little bit sluggish the more disks you add to the system or the more load that you put on the system? Or are you going to have a scale-out architecture that allows you to expand and have performance that is linear in nature and predictable? It really depends what you have existing, what sort of environment you have, whether it's brownfield, greenfield, what sort of strategy and plan you have in place to move forward. On the recoverability side, what sort of RPOs and RTOs need to be adhered to? Your recovery point objectives and your recovery time objectives. The applications that you are responsible for putting on these environments, how long can they be down? How long will it take to recover them? And how often do you back them up? These are things that need to be considered. Are there any SLAs in place for these applications? If these applications are down, do you have to pay any monetary fines or fees? Or what's the repercussions if these applications are down? Is there a business continuity plan? Is there a disaster recovery plan? These are things that need to be considered for every part of your environment. Not just the whole thing in general, but for every single part. Because it's not going to be the same for all of them. Some applications will have different RPOs and RTOs than other ones. Some may be local. Some may have to span across multiple sites. What about when you're looking at hardware? Do you have a DR plan for that? Or is it going to be a best effort 4-hour vendor support situation? It's very important to know what applications and what services are going to be affected by hardware that may go down. On the security side, are there any regulatory controls that need to be adhered to? Is the organization that you're with responsible to report to other bodies? Do you need to be a PCI compliance or SOX compliance, or do you have to have HIPAA or anything else like that? Do you or will you use role-based access control, where you have certain users that are only able to access specific things? And how do you actually map that out? Do you have a spreadsheet? Do you have it memorized up over here? Or do you just have super user, rest of users? For every component, again, this is very, very important to have. And not just to do it ad hoc, but to have a strategy in order to do it. Do you separate your management network from the rest of the network? What sort of considerations do you have to take into account? What happens if a management a device gets compromised? What sort of isolation do you have between the different components? Do you just have it on the perimeter and you have a soft GUI inside? Or do you actually have north, south, east, west firewalling based on the application or the device? All these things need to be considered. So some of the considerations for design. So those things that I showed you, those were the design characteristics. So now these are the considerations for design. Your requirements, your constraints, your assumptions, and your risks. So for your requirements, you have your business requirements and your technical requirements. For your business requirements, you may have something that comes down to you that says, okay, I need 10,000 desktops deployed by VDI, and they're all going to be task users. It gives you an idea of what you need to do, but it doesn't give you a lot of specifics. If you want to get the specifics of how you need to do those, then you have to look at the technical requirements. So your desktops must have Windows-based OS and have the resources required to support the line of business apps. So that gives you a bit more to work with, but doesn't necessarily give you specifics. So when you don't have the specifics, that's when you have to do something, which I'll talk to in a minute. That's when you have to create assumptions. But first, let's look at constraints. Some of the constraints that you'll run into are things such as perhaps the organization doesn't have a comprehensive Windows licensing availability or an ELA. Perhaps you're restricted to use very, very specific versions of Windows. What kind of budget is available for this project that's going to be done? How long is it going to take in order to do this? Do you have a certain window that you have to work with? What is the staff availability for the testing of this environment? How do you know that it's going to meet the requirements after it's actually done? Let's say, for instance, that one of the constraints you have is that you have no new hardware available for the initiative. How does that actually affect your ability to do this? Now, what I was talking about before is when you don't have all the information, this is where you have to make assumptions. So some assumptions you could make are that you have admin access to all the components of the environment, that you have adequate resources for the workload available. So previously, when it said that you have no new equipment available, you have to make the assumption that you have adequate resources for the workload available. If not, then it's going to have to go back over to the stakeholders of this project, and you're going to have to say, hey, I don't actually have what it takes in order to proceed with this. We need to either modify the scope of what we're doing, or we need to get those resources. So you don't start down the path of getting to the point where you can't proceed any farther. You've gone through the process of making the assumptions, responding back over to the organization, and saying, hey, I can either do this or I can't. This is what the missing pieces are. This is what I think it should be. These are the assumptions I'm making. Now, is it going to be a greenfield environment or brownfield environment? For the most part, organizations already have infrastructure in place, so it's going to be a brownfield environment. You're going to have to add something over to it. Now, when you're adding something to an existing environment, there's a lot of considerations that you have to take into place, such as is the resource that you're going, or the resources that you're going to put, or the workload that you're going to put on the environment, going to overtax the existing load or capacity of the infrastructure itself. Now, the only way you can really know that is to know not just what the trend is for the utilization of the infrastructure, but also what the spikes are. You know, are there certain spikes that occur during a month or during a quarter or during a year? You have to get all that historical information and determine whether you're able to put the new workload on that and not affect the existing production environment. So risks. Is the timeline too aggressive? Are other concurrent projects going on that may affect the ability to deploy the project? What about the config changes that are actually applied? If you have an existing environment and you're making some modifications in order to allow for the additional workload, how is that going to affect production? Is that going to go through a change management process? How do you vet the changes that are going to occur in that environment? What if there's a component failure? That's the big one. What if something breaks down? How do you know that something is actually going to break down? We'll talk to this in a little bit. Are there monetary penalties for SLA violations in production? So while you're building this environment to add on to the existing one, are you going to take down production and cost the organization a whole load of money while you're going through this process? If you don't go through each one of these components, or each one of these considerations and each one of these design characteristics, the availability management, performance, recovery, security, and requirements, constraints, assumptions, and risks, while you're going through the process of designing it, then you're going to run into issues along the way. So I'll talk to some of the different ways that you can look at an environment and the possibility that things may fail. Usually when you're looking at components, how do you really know it's going to fail? You may have an idea from similar components that you've had in the past that have a certain amount of lifetime. You may look at the manuals or what the vendors say the amount of lifetime for the component is, or you may just go on a certain life cycle for a piece of hardware. Often it's 3 years or 5 years, depending on the organization, and they don't even worry about the actual lifespan of the component. They just keep on recycling at a certain rate that's below that. So what we're looking at over here is what's referred to as the Kaplan-Meier survival curve. And it is a method of looking at how likely a patient is to, or let's just say we have some terminally ill patients, which would be our control. After a certain period of time, these patients start dying off until you basically get down to none. A control would be something like a clinical trial that's applied. So you have the control, which are not getting the clinical trial, and then you have the blue up on top of there, which is getting the treatment. You can map that out over a period of time to see if the clinical trial is actually working. You can see the difference between the control and the test subjects that are getting the treatment. Now, what if we took this concept and applied it to components? And a use case for this is, let's say that you have a client that happens to operate a mine, which I actually do myself, so I can talk about it directly. In mines, you have very, very different types of environmental variables than you do in a regular data center. You have different temperature fluctuations, a different kind of heat, different sort of ventilation. Sometimes there's a different elevation. Components seem to die a lot quicker in environments like this that are very, very dusty, very, very extreme, very different than a data center. So if you were to look at environmental variables as a treatment and the patients are the components, then you can use this similar sort of model in order to map out the specific environments that you're working with to determine how long your components are actually going to last. Now, this is not something that is easily attainable after a short period of time. This is something that would have to be managed over a long period of time. The benefits would not be seen immediately. They'd be seen after enough data is gathered, so you can say that, okay, this motherboard in this environment or this hard drive in this environment will last this long because we've looked at how long it lasts, we've looked at the specific environment variables, and we know we have the data. Therefore, we don't have to stockpile 10 motherboards, 100 drives, spend all that extra money in order to make sure that we have spares. We know a lot more now that we've gone through this process. So this is one aspect that you can use to determine the likelihood of a component failure using environmental variables, that is. Another thing that you can look at when you're building an infrastructure, designing an infrastructure, is what's referred to as defense in depth. If you want to ensure that your environment is going to stay available and resilient, then you can't just have one plan in place. You have to have multiple levels of plans in place. If something fails, you have to have a backup plan for that. If that fails, you have to have a backup plan for that. So for instance, in this model over here, I show application level clustering, ingress and egress load balancing, high availability software, fault tolerance components, and fail fast application architecture. Now there's more ways that you can do defense in depth, but if you apply these, then there is a good chance that your application, your service is going to be a lot more available, and if it fails, it will recover a lot more quickly. Graceful degradation is another technique that you can use to make sure that when something fails, that is not catastrophic or detrimental to your service or application. A good example of this is if you look at the flight control systems which are used in many planes. There's not one flight control system in place. There's, on average, 3 primary control systems. And then there's another 2 secondary control systems. The reason for this is that if the first primary control system goes out, you still have another one that you can fail to. If that goes out, then you still have another one that you can fail to. If whatever takes those control systems down is actually a bug that may be related over to the software or the firmware or something that's related specifically to the design of that control system, then you can go over to the secondary flight control system, which may be pared down a bit, but is a totally different design, totally different components, totally way of doing the same thing which the primary control system doing, which is keeping you up in the air and being able to land. So they go about it different ways, but they functionally provide the same thing. So by having the ability to fail gracefully, you're able to keep the service, which this service happens to be keeping people flying in the air, very important, up without any kind of downtime. Downtime in aircraft is pretty bad. So let's talk about risk mitigation. Usually when people are talking about risk mitigation, they are confronted with a single scenario. They'll say, okay, if this happens, then we'll do this. We'll put something in place in order to compensate for this possible problem. A lot of the times, it's not delved into very, very deeply. And a lot of the mitigation process is usually built up from experience or knowledge, things that are gathered from doing a root cause analysis on a problem that has occurred in the past. Root cause analysis, they only look backward. They allow you to increase the resiliency of your environment and the resistance to failure by doing an iterative process of fixing the things as they occur. But each time they happen, you're going to have an outage, you're going to have downtime. You have to fail in order to learn with this sort of model. Another way that you can look at it, instead of using that method, is what's referred to as fault tree analysis. If you look at, on top over here, subsystem A, let's say that subsystem A is a service. And over here we have some Boolean gates. The ones that look like a Star Trek symbol, those are OR gates, which means that if either one of the poles on the OR gates, an event happens on those, then that will bring subsystem down A, or subsystem A down. Now the AND gates, which are the ones that have 3, 4, 5, and 7 and 8, those ones have to have all of the inputs light up at the same time in order for that to affect. So if each one of those, 1 through 8, were different events that can occur, then if something happens with event 1, that will take down subsystem A. If something happens with event 2, that will take down subsystem A. If something happens with 3, 4, and 5, if it happens one at a time, it's not going to affect the subsystem. If it happens with all 3, 4, and 5, then it will. Now on the last one over here, if something happens to 6, it will take down subsystem A. If something happens with 7, nothing will happen. If something happens with 8, nothing will happen. If something happens with 7 and 8, then that will take down subsystem A. So by going through this process and mapping out all the possible things that could occur, you can look at how events are related and what sort of effect they'll have on other systems. So instead of just showing the gates over here, you can show that as different levels of components or services or part of a service, the different things that makes it run. If this happens over here, how does that actually affect the rest of the environment? And also by going through this process, you know what state your entire environment is going to be by looking at all of the affected dependencies. So if one of these occurs, then you can take that as a snapshot of a different state. You know what to expect. You know how to compensate for that. This method is a lot more in-depth than your regular risk mitigation process. This allows you to dive into many, many different levels of failure. They say that with an aircraft, for instance, going back over to that analogy, that more than 7 systems or separate systems need to fail before it causes a critical issue. Although, imagine with flight control systems, that would be 5. About 5 minutes. Okay, we'll go through this, rest of this quickly. A Venturi analysis is a different way of looking at it. It's kind of like looking at what happens next. If you look at the route that something takes, then you have to see whether a decision that happens at that point or the way that things go will change the outcome. For instance, if you're sending mail and there's an issue with DNS, then it may go over to either success or failure. Looking at the path of whether things fail or succeed, you're able to see what it maps out over to the final consequence. By looking at this model over here, you can see that if DNS fails, it means that it doesn't matter what happens throughout the rest of it, the mail will be lost. If the DNS succeeds and other parts fail, then you may have intermittent results. So this is important to see what actually happens throughout the different possible scenarios that can happen. Now, in the 1990s, in Cuba, the Soviet Union basically pulled out all of their financial support. And Cuba went into a massive depression, more so than the normal. They had no resources coming in, they had no money, they had no way of doing things. They had to be very, very innovative in order to get the basic necessities that they need. Now, one thing that they did have is they had a 1950s era washer and dryer, which unequivocally would always break, except only one part of it would break. They would take that broken part, which was a certain, it was the washing component, and they would take that motor out and they would turn it into different things, either a belt sander or a grinder or a different way of cutting cabbage or shoe sander, all sorts of different things that they could do from this broken part. They were able to look at the necessity of things and see what needed to be made in order to fit the situation. You know, this a term for this was coined objects of necessity or technological disobedience. Some other similar types of things that you may see or have heard of is called redneck engineering. So here they need a bridge, they had a school bus, gotta do what you gotta do. All right. So what's important to do is look at all the different components that you have in your environment and break them down, decompose the technology so you know what the individual parts are. By doing so, you would be able to understand what you can actually use those parts to rebuild certain services or applications if you don't have the means to go out and purchase new hardware or get more resources. A really good example of this is the Apollo 13 space mission. They didn't have any more resources. They had an oxygen tank that blew, and carbon dioxide was filling up within the space shuttle. They were able to scour through different components, look at all the different options that they had to rebuild that carbon filter. And when they were able to do that, they were able to make their way back home. So what is your infrastructure really made of? What are the different roles that your environment can be repurposed to do if something fails? And this brings us over to what I refer to as a juxtaposition of methodologies. Let me see here. Oops. So if you were to look at an over-engineered infrastructure, something that is built in a waterfall type environment where you have a plan, you follow that plan, it has timelines and so on, that will build you a very robust, very strong, very resilient environment. But when that breaks and you don't have the resources to fix it, you need to forget waterfall and start thinking agile. Can you repurpose some of the hardware that you have in order to provide some of the same services that you had before? All devices that are deployed in environments now basically have CPU, memory, network capability, and storage. You're able to take those raw resources, use container technology, use virtual machine technology, and you can recreate the components that have failed. You can rebuild the environment in an agile manner by reusing these resources instead of using the traditional components which were used to build up this infrastructure. So I've been told that I've run out of time, which is good because I'm on the last slide over here. Now, a lot of the stuff that I'm talking about is my take on how risk should be incorporated into design, how you should look at design from not just one method, but many, many different angles, many different methods in order to get a more comprehensive, more deep understanding of all the different things that can occur in your environment. Now, the book that I'm writing is called Designing Risk in IT Infrastructure. It's the second book in the series. The first one is called Foundation in the Art of Infrastructure Design, written by John Rashid over here. It's a fabulous book. It is essential if you're an architect or want to be an architect. I strongly recommend that you use that as a foundation of knowledge. I hope to add to that. We're creating a whole series of books, and a number of other books are coming out in over the course of the next year as well. So mine will be out in 2017. You can get more information at the itaseries.com. That is all that I have.